Hi, everyone, and warm welcome to Researcher's Desk. Today with us, we have Romain Figuière, which I warmly welcome you, Romain. Romain is 3 weeks off his PhD defense, and he's come to share the knowledge he's going to be also presenting for his committee, I'm sure. And he's come to present it to us beforehand, which is a real honor. Roman is going to talk with us about toxic chemicals, assessing risks, and what those risks are involved and mitigating them. And Roman, it's really nice that you're with us. I'm going to let you share screen, and once we've got that up and running, I'll turn my own camera off. But I'll be here in the background, ready to jump in if anything goes wrong. A warm welcome to Researcher's Desk. That's lovely. Your video, everything looks really good. So I'll turn my camera off, and I'm here listening. Welcome.
Thank you, Alasdair, for the nice introduction, and hello, everyone. Like Alasdair said, I'm a PhD student at Stockholm University in the Department of Environmental Science, and I'm working specifically on managing the risk of toxic chemicals. And I'm here today to make a short introduction to the world of risk assessment and risk management of those toxic chemicals. But before that, I thought it was nice for everyone to understand what I mean by chemicals. So we are all on the same page. So usually when I ask people what they understand when I say chemicals, the first thing that comes to their mind is this chemistry laboratory. So the chemicals that we researchers in the universities are manipulating in our labs. If people start thinking a bit more about what chemical can be, then they start thinking of pesticides, what's used on the fields to grow cereals and vegetables. They also think about pharmaceuticals, so what you're taking when you're sick. And they think about cleaning products, what you can use at home to clean. So these are also chemicals. But I want you to, like, for me, chemicals, it's much broader than this. Because chemicals are also used basically in every object in our life that you can find at home, in every furniture. They can be used on your couch, on the floor, on the walls, in the curtains, basically anywhere. And they're also used in all electronical devices. In your phone, for instance, there are many, many, many small pieces of plastics. Those small pieces of plastics are chemicals, and they contain other type of chemicals. In the batteries as well of your phone, these are chemicals. Same goes for your computer. Basically, chemicals are everywhere around us. And that's why the chemical industry like to say that they are the industry of industries, because without the chemical industry, the whole uh, industrial society that we know today cannot work. It has been even estimated by researchers that there are over 350,000 chemicals and mixtures of chemicals that are registered on the global market. That was back in 2020. And the chemicals industry are saying that they contribute to 5.7 trillions of dollars to the global GDP. So this is their number. I don't know if how true is that, but that's what they say. So that's why they call themselves the industry of industries. Um, so the question that you can ask yourself now is, how are we exposed to those chemicals? How do they enter our body? So there are three main ways of exposure for chemicals to enter in our body. Is either through inhalation, so through our lungs, through the air that we are inhaling, through ingestion, so in the food that we eat and the water that we drink, or directly through our skin. That's what we call the skin transfer or dermal exposure. And this can happen either at work, for people working in a lab, for instance, they're exposed to the chemicals they are manipulating, or people working in the industry, working with chemicals for whatever job that they could do. Or like this is another example of someone painting a car in paints. These are the chemicals that they're exposed to while working. But it can also be at home. I already mentioned the case of the pharmaceuticals that we are taking when we're sick. But like I said, in our food, there are chemicals. Some are wanted. There could be specific nutrients or food additives, but others are not wanted. Some pollutants, for instance. They are present in the drinking water. They're also present in the paint that you can use to paint whatever you're doing. In the cleaning products, like I said already, and basically in anywhere at home. For instance, can be on uh, in the air, indoor air, in the dust that is present inside your home. So basically, we're exposed to chemicals every day, all the time. So chemicals are permanently entering our bodies. That's a given, and that's not going to change. But then the next question is, how do they harm our bodies? What are the effects of chemicals inside the body? So they can basically act on every organs in the human bodies. So it can be the skin, the heart, the brain, basically anything. So they're all listed here. The effects of the chemicals can be immediate, meaning when you get exposed, you have an immediate effect. That's, for instance, an allergic reaction on your skin. That's an immediate effect of a chemical. Or it can be delayed, meaning that the effect that you see on yourself can happen hours, days, months, even years after you've been exposed to the chemical. A really famous example is cancer. Unfortunately, cancer can happen years after you've been exposed to a certain chemical that is causing the cancer to begin with. Those effects can be reversible. Again, if we take the example of an allergic reaction, it will last for a couple of hours, couple of days in the worst cases, but then you can cure it. While some other effects are irreversible. So cancer, in some cases, unfortunately, this is not reversible, or effects of chemicals on the reproductive system. Uh, some chemicals can affect fertility, and unfortunately, these effects are poorly reversible as well. So you have both type of effects. So then the next question is, are we all at risk? Because I said chemicals entering a body all the time. Some chemicals can have bad effects that are not reversible and in a couple of years from now. So does that mean that are we all gonna die? No. Spoiler alert, no. To understand that, it's important to distinguish between what is the hazard, what is the exposure, and what is the risk, and specifically the difference between hazard and risk. To explain that, I have a famous example that we keep using when we're teaching these type of things here at Stockholm University. You can take the example of a shark. A shark by nature it's a dangerous animal. Yeah. If you see a shark is dangerous. I think that's not new, but for us here right now in our Stockholm, we are not really exposed to a shark. So a shark is still dangerous, but we are not at risk from it because we are not swimming next to it, right? So, and then now you take the same shark, but now you're swimming next to it. So you're getting exposed to it. You're getting exposed to that potential hazard. And the closer you swim to the shark, the higher the risk. And with chemicals, it's the same. You have chemicals that can be extremely harmful, but we are not exposed to them at all because they are well contained, they're enclosed, the emissions are extremely well controlled and limited. and us as consumers, we are not exposed to them. So then there is no risk to our health. While others, which are like, let's say, for instance, pesticides, in some cases, they reach the water system, the water resources, and then we are getting exposed because we're just drinking water. Or they are like some pesticides are left on the food that we eat. So then we are getting exposed to them because in those cases the exposure are not well controlled. And that's extremely important to distinguish this when we talk about chemical risk, because that's what we try to illustrate here. A risk will be this combination between the toxicity or like the harmful effect of the chemical and the exposure intensity to how much of the chemical are we exposed. And for most of the chemicals, you can determine a threshold, meaning an exposure intensity below which there is no toxic effect. It means that the whole goal is to keep our exposure to the chemicals in that region below this threshold here. So then we're almost sure that we won't have problems. That's the whole goal in a chemical risk assessment and management. So the chemical risk assessment, the goal is to determine this threshold, and the risk management is to make sure that the exposure is below this threshold here. So how can we do that? There are several strategies, type of strategies. The first one and the easiest to understand is the wearing personal protective equipment. So this is mainly for workers. If you're working in a lab, for instance, you're gonna have to wear gloves, lab coats, a mask, goggles. All this is to make sure that you do not expose yourself to the chemicals. So the gloves and the lab coat is to prevent the chemical to enter your body through your skins. The mask is through ingestion and inhalation, and the goggles is to protect your eyes. And then here you have this drawing with all type of protective equipment that exist. They are not all relevant for chemical exposure, but that's the same idea. Then you can also encourage good practices. So that's why in some workplaces you have those signs that say that personal protective equipment must be worn in certain rooms. That's exactly for that reason. Or if we take an example at home, if you take any type of cleaners that you have at home, you most likely will see this type of label here that says that you have to keep out of reach of children, that you should not get in contact with your eye, skin, or piece of clothing, that you should wear gloves when you manipulate it, maybe sometimes a mask as well, for some type of cleaners. And I would highly encourage you to follow those piece of advice, because these are there for you to protect yourself from the chemical that you're manipulating. So these are important. Another options to control the risk of a chemical is what I call engineering control. So this is not for us in our everyday life. It's more for the industries themselves to change the way they manipulate the chemicals to make sure that the emissions are limited. And the easiest example to understand is the treatment plants, the water treatment plants. That's what they're trying to do, is to limit the emissions of those chemicals in the water, in the environment. So either for the wastewater treatment plants are there to control those emissions, and then in the other side, the drinking water treatment plants are there to make sure that in our drinking water there are no pollutants in there, so we are not exposed to the drinking water. All those measures that I just described, they are there to make sure that the exposure intensity is as low as possible. So then we are like in this region here to ensure that yes, we're exposed to some chemicals, but to a concentration that is so low that there are no toxic effects. Unfortunately, for some chemicals, this threshold here is so low that it's not possible to ensure such a low exposure. So then in those cases, the only possibility that we have is to change the toxicity effect. And what does it mean in practice? It means to substitute or to eliminate the chemical, to change the use of the chemical. So to replace it with something else. And that's what we call in my field of research, that's what we call the substitution of harmful chemicals. So the idea is to develop new chemicals to replace those bad ones, the ones that are extremely hazardous and that we cannot control, is to replace them with chemicals that are safer, either from the human health perspective or for the environmental perspective. And these substitution activities, they can be either voluntary. So these happen at these are the chemical companies that have to do that work. So they are the ones that need to make sure that the chemicals they're using are safe to use, right? So this substitution can be either voluntary, so a company can decide on themselves to say, we do not want to use chemicals that are hazardous for humans or for the environment, or it can be encouraged or even forced by chemical legislation, which can be at the national level, at the European level, or the worldwide. These are authorities that are forcing companies to substitute by restricting or banning uses of certain chemicals because those chemicals are extremely harmful and emissions cannot be properly controlled. So then the only option that we have is to restrict their use. So that's the theory. So in theory, we have a huge group of chemicals. Some are not harmful, others are harmful. If they are harmful, we can try to control their use so that we're not exposed to them. And if we cannot control their use, then we ban them and we replace them with something that is safer. In theory, all is good, right? So it would mean that we are all safe, right? The problem is that in practice, it doesn't work as that well. And to illustrate that, what it took the example of PFAS. I guess most of you have heard that term before. Maybe you don't know exactly what it is. So PFAS is a term to designate a group of chemicals of around 10,000 chemicals, which have a CF2 or a CF3 group in the molecular structure. So that's how I put an example here. So this is a molecular structure of one PFAS that is called PFOA that have this carbon fluorine bond in the molecular structure. So in that case, they have 7 carbons with these carbon fluorine bonds. Those PFAS, they're used in hundreds of different uses across many sectors in consumer products, meaning products that we can buy ourselves, but also in industrial uses. So here, that's a work that I've done in my PhD, where we try to map out all the uses of PFAS. So here you have like the use categories that we have identified. So you can see they're used in pharmaceuticals, they're used in building products, they're used in cosmetic products, electronics, and so on and so forth. And here you have the total number of use that we have identified. So we identify over 300 different uses of PFAS. This is just to tell you that PFAS are used everywhere, basically. They're used everywhere. The problem is that because of this carbon fluorine bond that they have in the molecular structure, those PFAS are considered as persistent in the environment. What persistent means, it means that once they are emitted in the environment, they do not degrade. Means that they stay in the environment and they can stay there for years and years and years. And I'm talking about 5, 10, 20 years, not just one. Huh? So what does that mean? If we go back to this curve that I took before, the problem with those persistent chemicals is that as the emissions continues, we continue emitting chemicals in the environment, because they do not degrade in the environment, the concentration in the environment is going to increase. It's going to increase and increase and increase until so that's what I try to illustrate here. The exposure intensity in the environment is going to keep increasing until eventually we get to that region here. It means that we're going to go above that threshold where there's going to be 100% of toxic effect, meaning there is going to be a really bad effects on our bodies. Some that are known, that are well known due to toxicity studies, and some that are unknown because we just didn't do the test. So it means that as the emissions of those persistent chemicals in the environment continues, we're going to increase the concentration in the environment, and that will result in an increasing probability of known and unknown toxic effects on us as humans. Because if the concentration in the environment increase, we'll eventually reach water or food, so we're going to be exposed via the water and the food that we eat and drink. And those consequences are irreversible, meaning that once we see the effect, it's going to be too late to try to remediate the situation. And the PFAS case is a really good example because right now this is a map that has been published 2 years ago now by this Forever Pollution Project, where they try to map all the contaminated sites with PFAS in Europe, and all the red dots that you see here on this map is all the sites that are where we know it is contaminated with PFAS, and all the blue dots are the sites where we suspect it's contaminated with PFAS. And basically what you can see is that everywhere in Europe is already contaminated. So we are already exposed with PFAS every day. That's a fact, and it's not going to change. So that's quite scary. And the other thing is that this safety threshold that I've showed before for some PFAS is decreasing over the years because we're doing more and more toxicity tests to try to determine what toxic effects PFAS have on our bodies. And that's a slide I saw from Veolia, a water treatment company. And they said that over the past 20 years, the safety threshold of some PFAS, not all of them, but some of them, decreased from the gram per liter in 2005 to the nanogram per liter in 2022. To give you an idea, 1 nanogram per liter is the equivalent of 1 grain of salt dissolved in an Olympic pool. So it's like nothing. It's extremely low. So on the one hand, it means that on the one hand, you have concentration of PFAS in water that is increasing. And on the other hand, you have this safety threshold I keep talking about that is decreasing. So what does it mean? It means that now we are at a point where the waters all around the world become unsafe to drink. And that's a paper that we published in our group a couple of years ago, where the researchers, they demonstrated that because of this safety threshold decreasing, and now the authorities are publishing safety guidelines value for drinking water that are lower and lower and lower, to a point where even the water in Antarctica and Tibet is unsafe for consumption. That's what you have here for the specific case of PFOA. Now, before you start completely freaking out and think that we're all going to die just by drinking water, I just want to reassure you this extremely low new value from the US EPA is based on an effect of PFOA on the efficacy of vaccines in children. In other words, it's not because we are drinking water that have a concentration of PFOA well above this value that we're all going to get cancer. It's not the case, and we are not all going to die either. It's still worrying, but I just want to make that clear. We're not going to die by drinking water. Yeah. Anyway, the whole point now with the problem with PFAS is that now they are found everywhere to concentrations that are getting unsafe for consumptions. And the problem now as well is that if we want to clean water, to remove all PFAS from water, has been estimated by some researchers that it will cost 100 billion euros every year to clean waters from all PFAS. So it's extremely expensive, and I would say impossible even. It's not even thinkable to spend that much money just for for cleaning the drinking water. So in my opinion, the only options that we have now is to stop emitting PFAS, and to stop emitting PFAS, it means stop using PFAS in the first place. So I'm advocating that we should just phase out the use of PFAS and we should start replacing them. And that's why you probably hear about several countries that are now trying to ban uses of PFAS. So I put some example here. In France, they are talking about banning the uses of PFAS in cosmetic products, textile, ski waxes. In Denmark, they're talking about banning PFAS in a piece of clothing. In the UK, they're also talking about banning all uses of PFAS. And the biggest activities in those terms at the European level, Germany, the Netherlands, Sweden, Norway, and Denmark are working together to propose a ban on all PFAS in all their uses. So they want the industry to completely stop using PFAS exactly for that reason, and to substitute them with something hopefully that is safer and better than those fluorinated compounds. Whether this restriction is possible, wanted, etc., that's what I'm working on in my PhD. I'm not going to go into details now, but if you're interested in those questions, feel free to get in touch with me. Because unfortunately, it's not that simple to say, oh, we want to stop using PFAS. But that's my whole research interest. So yeah, if you're interested, feel free to get in touch with me. And if you have questions, I'm happy to answer now. Thank you.
Thank you very much indeed for an absolutely super talk. There are so many wonderful things about that talk. Down to it's chilling to learn and understand more about PFAS. To being down to the beautiful pedagogy where you explain for us the difference between hazard and risk, which I think many of us get wrong. Thank you for being at Researcher's Desk.